Hi guys. In this video I will go over part of the Alkyne handout. I will go over section 3, which is hydration of an alkyne. We will introduce here the idea of tautomers, the process called tautomerization, the idea of tautomers. For example, these two here are tautomers of each other. We will see more about tautomers down below. The first method for hydrating an alkyne is shown here with under A. This hydration is a lot like an alkene hydration. We're using aqueous acid, such as sulfuric acid. You hydrated norbornene with sulfuric acid in the lab. With alkynes, we often include a mercury cation as well. This is different from alkenes. Alkynes are less reactive. The mercury ion is a little bit more electrophilic. You can hydrate an alkyne just using aqueous acid. In fact, we will do that in lab. We will not use the mercury salt. Of course, mercury salts tend to be toxic, and that's one of the reasons we're not going to be using it. Historically, mercury is included in this reaction. When we do the mechanism, I will not discuss the mercury. I will do it just with aqueous acid. But when you see this, you may often see mercury. You pretty much just need to be able to recognize that what we're doing here is hydration of an alkyne. Okay, when we hydrate, we're adding water. This structure has H2O added. You can look at the formula. H2O has been added to the formula. We've also got an OH here. There's also a new H on the N carbon. Here there's one. Here there's two. So we've added two H's and an O. When we hydrate an alkyne, we get an enol. What is an enol? It's an alkene with the OH group on the alkene. So the enol comes from enol, as in alcohol. And it's a blending of the ene and the alcohol into one word, enol. Now, enols are not typically stable. Some of them are, most are not. Enols will typically undergo a rearrangement process called tautomerization. Simply a rearrangement. Formula of this and this is the same. It rearranges to a carbonyl form. This is often called the enol form, and this would be called the carbonyl form, or sometimes the keto form, because it is a ketone. This is an equilibrium here between these two structures. In the equilibrium, usually the ketone is highly favored, predominantly, such as 99.99% to 0.001% or whatnot. So if we back up and look at this again, if you hydrate an alkyne, the product here is this ketone. And the formula here has H2O added to it compared to the original formula. But there's no OH. It's actually a carbonyl. The two new H's are actually on the N carbon. Here there's one H on the N carbon. Here there's three on the N carbon. Okay. We'll go through the mechanism and then we'll clarify further what are tautomers, and we'll look at the mechanism for the tautomerization. First step, again, I'm not going to include the mercury in the mechanism. H plus, and water. Okay, we've got two pi bonds, twice the fun. Pi bond attacks H plus. Where are we going to leave cation? On right or left? Well, it would be left, because we have this sp3 carbon that can inductively donate. This would be a secondary carbon, where that would be a primary carbon. We're going to leave the cation on the left. So this pulls away and attacks here. Boom, boom, boom. Okay, we got to be careful here. That's two carbons and it's linear. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. H. I'm going to draw them both in. But we still have a double bond, because only one pi bond reacted. One pi bond reacted, leaving the other pi bond there, but now we have a plus charge here. Okay? This is just protonation of the pi bond, or reacting to the pi bond with the proton, or H plus. Now, I drew this as zigzag. I drew it sort of trigonoplanar. It's actually still linear. That carbon is still sp linear. Alright? Next, water attacks cation. These electrons add to cation. That's going to give boom, boom, boom. We now have oxygen bonded there, two H's, one lone pair remaining, and positive charge on oxygen. Okay, the two new H's are here. I'm not going to draw them in anymore. I'm sorry, it's not two new H's, it's one new H. The other H was there at the beginning. But the two H's are here. Water adding gives this. Now we need to remove an H. There's got to be a minus here. If it's sulfuric acid, we can use the bisulfate anion, or we can just use water to take the H. These electrons bond to H, these electrons move on to oxygen, and that gives the enol. Plus, it reforms H3O+. It reforms acid. It's a standard hydration of a pi bond, regioselective. We're going to make cation here. That's why the OH is bonded here. We still have a double bond. That's an enol. Okay, the enol is not stable. It undergoes a rearrangement. Mechanism for the rearrangement, okay? We need to know a mechanism for this. It's not just magic. What do we need to do here? We need to remove an H from the oxygen. It's gone. We need to put an H on this carbon, because here there's two, but there's three. Ultimately, we need to relocate a single hydrogen somehow. This gets us to the definition of tautomers, which is shown up here. Or the process of tautomerization and going from one to the other. Tautomerization involves relocation of a single hydrogen and relocation of at least one pi bond. If you look at this, the pi bond is between the carbon and carbon. It has been relocated to be between the carbon and oxygen. So the definition of tautomers or tautomerization has been met here. These are tautomers of each other. What's the mechanism for this? Keep in mind we still have acid, H+. We have an alkene. Has an alkene ever reacted with H plus in this class? Yes, plenty. Where are we going to leave cation? Left or right? Left. It would be a secondary cation. Let's look at that cation. This attacks here. We get boom, 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 boom. New H there. Cation there. Nothing really new here. Alkene attacking H plus, cation here. Think about it. Don't we need to add an extra H to this carbon? Yes, there's now 3 here. We now have 3 there with that H added. Next step. We have resonance here. Just like we saw on the previous page in this reaction here. We can draw a resonance structure. These electrons can move down, and that gives boom, 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 boom. We now have double bond to oxygen. I'll draw that bond out. 1 lone pair left, and now the positive is on oxygen. Resonance, and we're using the double-headed resonance arrow to show that we're doing resonance structures here. Now look at our structure though. The resonance structure gives us the double bond. What do we need to do to get home? We need to remove the H. Well, there has to be a minus here, or again we could use water. These electrons bond to the H, these electrons move here. That gives the final product, the ketone, and we reform our acid. The tautomerization, we showed a mechanism, but it's acid catalyzed. Starts with the acid, but we reform acid. That's H plus in water. The tautomerization is in equilibrium. We can go backwards. If we had a carbonyl, we could protonate it. We could show that resonance structure, and then we could remove the proton. We'll be doing more of that later in the course. But again, the equilibrium favors the ketone, or the keto form. Okay. There's your hydration of an alkyne to give the enol, and then the enol undergoes an acid catalyzed rearrangement to the keto form called tautomerization. These two, the relationship between these two are tautomers, because in going from one to the other, all we've done is relocated one hydrogen and at least one pi bond. Okay. The tautomerization mechanism, a good way to remember that is the mnemonic Oreo. Now this is not going to be found in any textbook. This is actually something that yours truly sort of made up. I think it's useful. What does Oreo stand for? It depends on if we're under acidic or basic conditions. If we're under acidic conditions, it stands for, I'll go back up here, H plus on. This is the steps of the tautomerization. What did we do first? We put a proton on. Okay? On. After we put the proton on, there's the proton we put on. What did we do next? We showed resonance. Now, resonance is not a step. Okay? Not a step in chemical life. Resonance is only a step on our paper. That is, in this mechanism, this is one intermediate. That's not two different intermediates. It's one intermediate. We're just showing two different sort of forms of that intermediate. That's the idea of resonance. We put a proton on, we showed resonance, then what did we do? We took a proton off. Another O. Off. Oreo. On, resonance, off. That's your mechanism for tautomerization. Any tautomerization. Acid catalyze. Now if it's base catalyzed, and we'll do that on the flip side over here where we have base when the tautomerization takes place. Under basic conditions, it's just the opposite. Because bases take off protons, and so it's off, resonance, and then you put it back on. But it's still Oreo. This works for any tautomerization you will ever encounter. Okay, more on recognizing tautomers. Which of the following are tautomers of the compounds shown in the box? Label them as either an OH tautomer or a CH tautomer. Back up here. The enol is considered an OH tautomer because it has the OH. The keto form is considered a CH tautomer because the H here is on the carbon. We're dealing with the H that's being relocated. Here the H is on the oxygen, here it's on carbon. OH tautomer, CH tautomer. So label the tautomers as either OH or CH. Okay. I'll let you do that one on your own. Next question. Are the following tautomers? I'll let you do that on your own as well. We'll answer these in class. Finally, tautomers can be more broadly called or considered what? Are they enantiomers? Are they diastereomers? Are they resonance structures? Or are they constitutional isomers? So we can broaden out our definition here a bit and make sure we can understand the relationship between what tautomers are and what these four things are. Okay, again, we'll do these in class at a later point. Okay, we can also hydrate alkynes using our hydroboration oxidation method. You remember with alkenes, this was a way to hydrate an alkene in an anti-Markovnikov manner. Same type of mechanistic ideas apply here. Two steps. First is with BH3, followed by a second magic step. Let's do this. We've got BH3, which is electrophilic. The pi electrons attack boron, leaving cation on the left. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's an H here. And now there's a boron with 3 H's. And that's a minus charge. And we have 1 pi bond left. plus charge here. Okay, do you think this is actually formed? The answer is no. Not actually formed, because at the same exact time the boron is throwing these electrons, the H minus here, and that's going to give boom, boom, boom. H here, BH2 here, and the new H here. No intermediate. This reacts with BH3 to give this structure. We just hydroborated the pi bond regioselectively. The boron's going to end up here, the H will end up here, all sort of dictated by the fact that the cation would be here if it had formed, but it's not actually formed. This is in step 1. Note that the boron and the new H are on the same side, because if the boron is positioned this way and it throws an H, they have to be on the same side. So this is a syn addition of BH3 to the pi bond. Okay, what does the magic step do? As we know from alkene chemistry, it replaces the boron with an OH. Under my finger is a boron. Now it's an OH. There you go. And when we replace that with an OH, we now have an enol. Now the new H is here, and the original H is here. All right. What do we know about enols? Typically, most of them are not stable. In organic 2, we will see some enols that are stable. Most are not. This will undergo a tautomerization. Tautomerization to another tautomer. What will the tautomer look like? In general, enols tautomerize to a carbonyl form, because the pi bond ends up, instead of between the carbon and carbon, the pi bond ends up between the carbon and oxygen. Then we relocate one hydrogen. So, I'm going to leave it up to you to draw in the final structure after the tautomerization takes place, and to answer the question here, what functional group will we have? And you can put the name of the functional group there. On the previous page, we had a ketone. Mechanism. All right. The mechanism in this case is base catalyzed, because during step 2 forms this, but as soon as it's formed, it continues on. The hydroxide is still here as it continues on. Hydroxide's a base. Since it's base catalyzed, the mechanism is, of course, Oreo, but it begins with taking a proton off, then we do resonance, then we put the proton back on. The off and on are standard acid-base chemistry mechanisms. Resonance, this resonance we had done before. The resonance you need to do over here in this tautomerization mechanism may be a little bit newer to us. Give it a try. We'll look at this mechanism in class and answer these questions here. Okay. Next, let's look at reduction of alkynes. Chapter 9.5 in your Alkyne textbook. Reduction by hydrogenation. Okay, if we have an alkyne, we can hydrogenate it. Hydrogen, precious metal catalysts such as nickel, palladium, platinum, etc. Very simple, straightforward reaction. We're adding an H to each carbon. Importantly though, how does hydrogen add? It's an addition, correct? The H's are shot in from the metal catalyst. Okay. This product is cis. We can draw in the H's. Boom. The undrawn H's are like that. They're cis. That is the metal catalyst sitting here. And then we shoot an H in here and an H in here. Same time. Now this is not a mechanism. I'm just trying to illustrate that the two H's are come in here at the same time. They're going to be on the same side, just like we've seen before. That effectively removes one pi bond and creates two new sigma bonds. Of course, carbon has 4 bonds, carbon has 4 bonds. But you see we've got a pi bond left. Okay? Of course, that's cis. You would not get trans here. The two methyls would not be trans, only cis. But this reaction will continue on. Typically something in brackets mean we do not isolate it, or it cannot be isolated. Just like up here. You typically cannot isolate the enol. It will continue on. You cannot isolate it. Down here, cannot isolate this. Because what do we know about alkenes? Alkenes react with hydrogen. We can just repeat the reaction. We come in with another H and another H. We now have 2 H's on each carbon. And if you look at that, it now becomes the alkane. We've reduced one pi bond, and now we've reduced the second pi bond, all the way down to the saturated alkane. 2 degrees of unsaturation, 1 degree of unsaturation, totally saturated with hydrogens now, when we come in with the other 2 H's. Now in this scenario here, this has stereochemistry because it's a stereogenic alkene. There's no stereochemistry here. It's just a simple alkane with free rotation. No stereochem to consider. Okay, now an example of this is shown over on the flip side, on the back of this handout, right here. This is the drug synthesis. You can read about it. I've given you the intro page here. Making compound 1, and you see we have these 2 saturated carbons here, CH2, CH2. In this drug synthesis, they're actually making this carbon-carbon bond. I'm sorry, they're not. They're not making that one. They're actually making that bond here. I reckon I'll highlight that. And they're making it from the alkyne, and the end carbon is coupling with this carbon. It's called a coupling reaction. You can look this up on Wikipedia. It's a palladium catalyzed coupling reaction. Very important type reactions in advanced organic chemistry. This is the bond we just made. Carbon-carbon bond. But then here they want this to be saturated, so they reacted with hydrogen, palladium on carbon, and they're hydrogenating it. It's a double hydrogenation. Okay? Double hydrogenation. all the way down to the saturated alkane. They're taking advantage of this sort of common reaction of the alkyne, but then they don't want an alkyne in their product. They apparently want the alkane here, and they get it by reducing with hydrogen. So, what if we wanted to stop with the cis-alkene? Could we? The answer is yes. There is a way to stop at the cis-alkene. And we can do that simply by using what's called a poison catalyst. Still with hydrogen and a poison catalyst. A poison catalyst is where a traditional catalyst, such as palladium or nickel, etc., has been treated with some type of so-called dopant. And the dopant, or the additive it's called, sort of diminishes the reactivity of the metal surface. It's well known that heavy metals will diminish the activity, such as barium, and maybe like barium carbonate, or lead does this, and you can add lead sulfate. These mixtures are less potent of catalysts compared to just the pure palladium. A common poison catalyst by name is Lindlar's catalyst. Anytime you see Lindlar's, that's a type of poison catalyst. This, I believe, is palladium with maybe barium or lead salts added. It may also have a tertiary amine, maybe like quinoline. Tertiary amines are known to sort of bind to the metal surface a bit and sort of diminish the metal catalyst. So Lindlar's is a very common type of poison catalyst. And so if we hydrogenate an alkyne with hydrogen and a poison catalyst, we can stop at the cis-alkene. This sort of implies that the first hydrogenation is easier than the second. And that's why we're able to stop here. So down here we just need one equivalent of H2, but up here we use two equivalents total. One equivalent took us here, but then it continues on because it won't stop. Down here it will stop. And in fact, if you had an alkene, hydrogen and a poison catalyst will not do anything to it. So it will not, you cannot do that reaction here. You would have to use a regular catalyst if you wanted to reduce this. So, in the end, we have a synthesis of a cis-alkene. And you can put this reaction in your toolbox. How do you make cis-alkenes? One way to do it is to partially hydrogenate an alkyne using hydrogen and a poison catalyst. Okay. The next question becomes maybe, well, how do you make transalkenes? Can you make a transalkene from a alkyne? That brings us to our next reaction. Partial reduction of alkynes to transalkenes using sodium and ammonia. Now this is our first look at a radical reaction. Here ammonia is used as solvent. Ammonia is a gas at room temperature, but at negative 33 degrees Celsius, it's a liquid. And so this reaction is done. The gas can be condensed into a liquid at this cold temperature. And then to the liquid, we add sodium metal. That's an oxidation state of 0. That's not an ion. Sodium metal. This combination will partially reduce the alkyne to the transalkene. This reaction is called a dissolving metal reduction because we begin with a metal, but as the reaction progresses and at the end of the reaction, the metal is dissolved. It's also, of course, a reduction. What have we done here? We've added 2 H's. There's a new H on each carbon. And anytime you add H's, that's a reduction. Let's look at the mechanism of this reaction. Now if you take sodium, you put in ammonia. What do we know about sodium in terms of electrons? Does it like to accept electrons or give them up? The sodium likes to become Na+. And indeed it will. And it gives up an electron. We can show it like that. I may also show it as a dot. This gives up an electron, becomes sodium plus, like it likes to become. Now has the electron configuration of neon. But so the sodium has been oxidized. What gets reduced here? Well, really nothing at this point. This is a fascinating sort of phenomenon that takes place. The ammonia solvates the electrons. Almost like hydrogen bonding to it. It's like a free electron that's sort of just in this solution. It's quite fascinating. The color also becomes blue, which is traditionally an indicator of a radical. Not always, but radicals, free electrons, these things tend to have interesting spectral properties and often are colored. There's some YouTube videos about this out there. I think I have one linked on my page. Ultimately, we have these solvated electrons. From there, one of these electrons will add to this pi system. I'm going to call it a dot. Now, typically, the electrons attack something. Here, for the first time, we see electrons coming into the pi bond. Also, whenever we move a single electron, we do a fishhook arrow. Kind of one barb. On the other hand, if we move a lone pair, okay, we do a regular arrow. What we have here is this electron will pump in here. At this point, both carbons are the same, so it doesn't matter which side, but I pump one in to that carbon, and the bonding pair I'm going to move over here. What does that give? It gives, well, this moving over puts a lone pair here. And over here we pumped in just one electron. Now we got two methyls. Will they be cis or trans? They will actually be trans here. And I'm actually going to redraw this lone pair sort of over here, just in terms of spacing. It looks a little better, like boom, boom. Because this carbon is now sp2, trigonal planar, boom, boom. That's an orbital here with a lone pair. Why trans? Why trans? Well, it had a choice. These groups could go one way or the other, just like a rotation. Which is going to be preferred? Trans is preferred. The two groups being trans is just preferred geometry. Back over here, these two methyls did not have a choice. They had to be cis because the H's came in and pushed them cis. Had a choice. We get to this point. By the way, we have charge. That is a negative charge. That carbon's negative. That's neutral. Of course, if you have a neutral compound and you add an electron to it, we should now have a negative charge because you added a negative charge to the neutral. There it is. Okay. At this point, this carbanion is very highly basic. It will take an H. We got an add an H. There's a new H here. Where does it get an H from? The only place it can get it from is ammonia. And so we have a case where ammonia serves as an acid. And we have a new H here, still an electron there, plus, what did we just make here? NH2 with two lone pairs, second lone pair, and that's a minus. Now at this point, this is going to want to accept another electron. So another electron pumps in here and teams up with that one. The second electron comes from the second sodium. Each sodium gives up one. So ultimately we need two sodiums. This is going to give boom, 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 boom. Now we have a lone pair and we have a carbanion. From here, we just need to add another H. We can come in with another equivalent of ammonia, and these electrons take the H, those stay behind, and we get our product plus another NH2 minus. So we've added an H to each carbon, in this case through acid-base reactions. We're not using hydrogen gas here. This is an acid-base reaction, acid-base reaction. But what we have here is these free electrons are pumping in, then it picks up proton. Pump another one in, then that picks up proton. If we completely balance this reaction, we see that we use two sodiums, and thus we produced two sodium pluses. We also produced two nitrogen anions. So in terms of balancing this, we need two sodiums, we need two ammonias, 1, 2. We make one alkene plus two NaNH2s. 2 sodiums on this side, 2 sodiums on that side, 2 nitrogens here, 2 nitrogens here, 6 H's here, 4 H's here, the other 2 H's are here. Now I have to point this out. You guys tend to not be able to recognize ionics. This is ionic. When we see this, this is Na plus NH2 minus, right? But we have 2 of those. That means we have 2 sodium pluses. And we have 2 NH2 minuses. Right? But typically ionics, you can just show it like that, just like if we were to show sodium chloride. I mean, that's sodium plus Cl minus. Okay. So, for your toolbox, what's a way to make transalkenes? Well, one way, and the only way we know so far, is to partially reduce an alkyne using sodium and ammonia. By the way, when this reaction's done, these ions are dissolved. They're all dissolved in the ammonia, and so the metal has dissolved. That's why it's called a dissolving metal reduction. Also, by the way, you can use other group 1 metals here. I believe potassium works just the same. Sodium is more common. Again, it's our first look at a radical reaction. But it's not completely radical. It's a mixture of radicals and ions. Radical, ion. In some cases, we may see radical reactions where everything is radicals and there are no ions. But we do have ions here. Okay, guys. The last topic on this handout is acidity of terminal alkynes. I think I'll go ahead and cover this here, and this will finish up this handout. If you remember from hybridization, the H on a alkyne here has some acidity. The pK is about 25. Now that's very weakly acidic, but it's more acidic than an alkene or an alkane hydrogen. We can deprotonate this, and we can make the resulting conjugate base, or the so-called carbanion. What bases will do this? Well, sodium hydroxide is not strong enough. 2 bases that are strong enough are shown here. One is N-butyl lithium. N-butyl, normal butyl or straight chain butyl. Boom, boom, boom. It's a straight chain carbanion. And then the lithium is the cation. That's N-butyl lithium. It's one of the strongest bases we'll ever encounter. It's a carbanion, very highly basic. The carbon does not like being minus, but you can have such a base. You can generate it. Strong base. These electrons will take this H and leave these electrons behind. And when we do that, we have the carbanion. The lithium can sit with it, but then right here we're making butane. Of course, there's 2 H's here, but now there's 3. Okay. Now if we look at the pKa's, that's 25. Butane is 40. Which side's favored? The weaker acid. Okay. So this side's favored by what? 10 to the 15. Or at least, depending on what this greater means. It's favored by more than 10 to the 15. That's a pretty large number. Highly favored. That means that n-butyl lithium is going to fully deprotonate this alkyne and take you to this side, and we can generate the alkyne anion. We could call this an alkynide. Alkyne-ide, like chloride or hydride anion. That term is not used much anymore. Typically you'll hear these called acetylide anions. Acetylene is the simplest of alkynes, but sometimes this name is used more generically for any alkyne carbanion. Okay. Why is this side favored? Other than, I mean, why are the pKa's like this? Because that's an sp3 carbanion, but now we have an sp carbanion. Lone pairs in an sp. And the lone pair being in an sp orbital is much more stable. That's why this side is favored. We've got a more stable carbanion. So ultimately we used one carbanion to form another. But the one we used is much less stable than the one we generated. Okay, another base we can use is actually one we just saw, NaNH2. That's a byproduct in the reaction above, but you can buy that compound, and that NH2 minus can act as a base, just like hydroxide minus. These electrons take the H, these electrons stay behind. We generate the sodium acetylide anion, because we're using sodium here, plus ammonia, right? This takes an H, ammonia. Hopefully you guys are not just sort of relying on some type of memorization to know that you produce ammonia here. You see that from your mechanism. That's now bonded to H, one lone pair left. Yes, there's a lone pair there. Okay, ammonia has a pKa of about 35. You can see that in the list of pKa's in the back of your workbook. This is 25. Which side's favored? This side. Favored by 10 to the 10. That's still over a billion. Still highly favored. And so, since it's favored, we see that this compound, which is sometimes called sodomid, that's sort of a two-word combination, sodium amide. Sort of the NH3 is the simplest amine. If we make an anion of an amine, we can call it an amide. So it's like sodium amide or sodomide. Now you got to be careful, because an amide is also the name of a functional group, carbonyl containing functional group. Okay. By the way, as an aside, in practice sodomide is a terrible base. You will probably never use it in lab. It was more common 50 years ago, 100 years ago. There's much better bases now. The problem with sodomide is it's not soluble in organic solvents. And you can't use water. If you use water, if you think about it, water has a pK of about 16. The base will take this H before it takes that H. And you'll just make hydroxide. and hydroxide is not strong enough to remove this H. That takes us to the next entry. If we tried to do this with hydroxide, like sodium hydroxide, I mean, you could show the acid-base reaction. We produce that plus water, but then you evaluate and you say which side is going to be favored, 25 or 16. Well, here, this side's favored by 10 to the 9, which is a billion. That means for every billion of these reactions or molecules, only 1 out of a billion is converted to the anion. That's essentially nothing. That tells us that hydroxide is not a strong enough base to deprotonate this in any practical manner. So hydroxide will not do this. But actually, though, let's consider the reverse. What if you had a carbanion and water? Would these react? Certainly they would. The reverse would happen. Because this can act as a base and take the H, and you get here plus hydroxide. Which side's favored? We said this side's favored. This will readily react to put the H on. That's the basis for this reaction shown here. Historical relevance, 100, 200 years ago, before batteries came along, miners used to use so-called calcium carbide lamps. Calcium carbide can be obtained pretty regularly from sort of like coke, calcium hydroxide or calcium oxide, and carbon. Sort of an old-fashioned reaction. This can be easily produced from ores found in the earth. What's the structure of calcium carbide? It's just Ca plus, or 2 plus, right? 2 plus. That means it's 2 carbons, 2 minus. Well, the structure is here. There's calcium carbide. It's the dianion of what we were forming up here. It's just got the anion on both sides. Now, what happens if you treat these with water? The same thing happened up here. This will take an H and put the H back on. Well, this does it twice. I'll just show it once. This takes the H, puts here. That takes the H, okay. So of course you need 2 equivalents of water, and you're going to get acetylene, which is H. It's the simplest of the alkynes in terms of an all-neutral. It's a gas. Flammable gas. And acetylene is commonly used in torches to produce a flame. Of course, the calcium is still here, and we produce hydroxide, 2 hydroxides. And this gas can be burned in sort of a chamber, and it can be lit well, let me back up a little bit. The chamber is filled with the calcium carbide, and then you add in water. I think it's a 2-part chamber, and the water sort of drips or moves over to the calcium carbide, and when they combine in that chamber, it produces this gas. The gas can come out, and you can light a match or something, and it will burn sort of like a pilot light will burn. And probably you can increase the rate of the reaction and make the flame larger. But basically now you have sort of this lantern that you can carry. Because again, this was common before batteries were sort of invented or were commonplace. Now there's actually a video on the YouTube page where someone shows how this works. They grind up the calcium carbide, they fill the chamber, and I think they then light it. But this is all based on this chemistry, and it's really the reversal. Instead of deprotonating like we were doing up here, we're actually protonating with water. Because again, carbanions, these acetylide anions are basic enough that they will react with water to become protonated, which is the reverse here. Now, as stated down here, we will react these acetylide anions as nucleophiles during test 3. And at that point, I'll remind you of how we formed these, and right here is how we formed them. 2 common bases used to form the acetylide anions. Okay guys, that finishes up this handout. We will maybe look at some of the miscellaneous things here in class. Some synthesis here. By the way, right here, what are they doing? 19 to 20. What are we doing right here? Okay guys, see you soon.